Let's consider valence bond theory. Now the word valence just means we use the valence electrons around atoms. Electrons coming from the highest n value being the principal quantum number. So let's, as an example, use the water molecule. So we draw the Lewis dot structure for water. There are 4 total electron pairs around water. Two bonding and 2 non-bonding electron pairs. The oxygen atom has to have at least 4 orbitals around it, because each electron pair is going to occupy an orbital. Look at the valence shell of the oxygen atom. We have the 2s and the 3 2p orbitals. That's 4 orbitals total. Now these orbitals can combine together. If we just add the orbitals together, just like we add functions, we can add the 3 orbitals together and we'll get 4 total orbitals. So we combine the 2s and the 3 2p's into 4 total orbitals. And if we combine these orbitals, then they will point to vertices of a tetrahedron. They correctly predict the tetrahedral geometry of the electron pairs around oxygen. And so when we combine orbitals, we have a specific notation. So we call Sp3 notation. That just means that we have combined or added together the 2s and all 3 of the 2p orbitals together. So we have the 3, meaning all 3 of the 2p orbitals were included. And these orbitals look something like this. And I'm not a very good drawer, but they would point to the vertices of a tetrahedron. And so we'd have the oxygen atom right in the middle. We have the hydrogens here. And then we'd have the lone pairs in 2 of the orbitals. Now one thing we want to keep in mind is we're combining orbitals to account for the non-bonded and bonding electrons for single bonds only. So as an example, consider carbon dioxide. This is the Lewis dot structure of carbon dioxide. So if we look at carbon, it has 2 single bonds around it. So we need only 2 orbitals from the valence shell. So we take a 2s and only 1 of the 2p orbitals. That gives us 2 total orbitals. So we don't have any non-bonding electrons around carbon. and we have 2 single bonds, so we just need 2 orbitals. And so that would be an s and 1 p orbital. So we have sp orbitals around carbon. What about the other 2 p orbitals? We've only used 1, we have 2 left over. Well, if we combine 1 s and 1 p orbital, then they would point 180 degrees away from each other, and it's the correct linear geometry for carbon dioxide. But now we have p orbitals left over. P orbitals have this shape, and so if we look at oxygen, these are the p's. I'll shade the p orbitals, and these are the sp orbitals here. Look at the oxygen atom. We have 2 lone pairs and 1 single bond around oxygen, so that's 3 total. So for oxygen, we need 3. That's a 3 orbitals. So we can take an s and 2 of the p's. So we'd have a p left over on each oxygen. So one of the sp2 orbitals would point toward the carbon atom. The other 2 would point away. In a triangular trigonal pyramidal geometry, because we have 3 electron pairs around oxygen. Then we have the unused p orbital, which I'll shade here so we can see it better. So the unused p orbitals can overlap with each other and produce the second bond, or the double bond. So the double bond is formed by overlap of the unused p orbitals on I didn't spell orbitals very well. Orbitals on carbon and oxygen. Now we only used 1 p orbital on carbon to form the sp orbitals, and so we have 2 left. We used 1 for bonding with the oxygen on the right. We can use the second for bonding with the oxygen on the left and its unused p orbital. So we have double bonds to both oxygen atoms from carbon. These orbitals, say the sp3, sp2, sp orbitals, are called hybrid orbitals because they are made from the atomic orbitals. So they're hybrids. This is a way of modeling electrons in orbitals like we have on the hydrogen atom that we studied before. So remember, count single bonds plus non-bonded electron pairs And that will equal to the total orbitals, total hybrid orbitals needed, and then just combine orbitals as needed. If you have 2 total electron pairs, you would only need an S and a P. If you have 3 electron pairs, you would need an S and 2 P's. And if you have 4 electron pairs, you would need an S and all 3 of the P orbitals. We write this as a superscript. It's not actually P cubed. It's just a linear sum, S plus P plus P plus P, to make the hybrid orbitals. These are hybrid orbitals made from the original atomic orbital. Say we have, like sulfur hexafluoride, we have 6 bonding electron pairs. Well, where are we going to get 2 more orbitals? Well, we can get them from the d orbitals. So, if we have 5 electron pairs, we can use an S, all 3 of the P's. That gives us 4 total. We need 1 more. We can take one from the D shell. Then if we need 6 pairs to accommodate, we can take an S, all 3 of the P's, and 2 of the D's. These are only possible for third row atoms and below, because only they have d orbitals available. The principal quantum number n for d orbital starts with n equals 3. So we have to be on the third row or below to have d orbitals.